In this video, I'm going to talk about the variance of the errors in simple linear regression. So I have an example here to illustrate the variance, and we're going to think about the assumptions that underlie simple linear regression. So we can summarize the assumptions by saying that the errors in simple linear regression are independent normal random variables with zero mean and constant variance. And so we're going to think about that constant variance. So here's a scatter plot of an example data set. I have 20 observations of y1 and x1. And I fit a simple linear regression model to the data. So that's the red line through the data here. And it has equation given up here. 1.930 is the intercept, 0.9927 is the slope. And let's think about the first observation, y1 equals 10.9, x1 equals 8.6. That's this observation up here in the top right corner. If I plug x1 equal 8.6 into my estimated regression equation, and I do the math, I get 10.5 for y hat. The fitted value of y for this first observation is 10.5. And then if I take the difference between 10.9 and 10.5, I get 0.4. And so that's the residual for the first observation. And on the graph, that would be the vertical distance between the observed value of y, 10.9, and the fitted value of y, 10.5, which is on the line. That distance is 0.4. So that's the residual for the first observation. I could do the same kind of calculation for all 20 observations, and it would give me the residuals. If I was to square those residuals and then sum them, I get something called the sum of squared errors. It should be called the sum of squared residuals, but we could think of it as the sum of squared errors. That's the more usual terminology that's used here. If I take that sum of squared errors and then divide by n minus 2, so n in this case is 20, so n minus 2 is 18. So the sum of squared errors divided by n minus 2, that gives me a quantity called the mean squared error. And that mean squared error is an estimate of the variance of the errors in this simple linear regression model. And you might be thinking, well, usually when we calculate a variance, we would divide by n minus 1, not n minus 2. So why n minus 2? Well, the reason is because we're estimating two parameters here, the intercept and the slope. So we end up losing 2 degrees of freedom when we estimate the variance. And so that's why we divide by n minus 2 instead of n minus 1. That's the mean squared error. That gives us the estimated variance of the errors. If I take the square root of the mean squared error, I get the estimated standard deviation of the errors. And the notation that's used here is that the square root of the mean squared error is equal to capital S, and that's given over here in this Minitab graph output. And the terminology that's used here is S is called the regression standard error, or sometimes the residual standard error. So Minitab is telling us that S is 0.538193 in this case. The Minitab does the calculation for us, but for illustrative purposes, to understand where that number is coming from, I'm just going to run through the calculation kind of by hand. So if I fit the regression model, and then if I click the storage button, and I'm going to store the fits and the residuals. Here's the fits, the y-hats, and here's the residuals. And we can see there's the 10.5 we talked about earlier, and there's the 0.4 that we talked about earlier. Now, if I do a calculation, I'm going to calculate the sum of squared errors. So it's the sum of residuals squared. So there's the sum of squared errors 5.21372. And it's also given up here in this output here in the analysis of variance table, in the sum of squares column and the error row. There's the sum of squared errors there, 5.214. And then if I do another calculation, so this time I'm going to calculate the mean squared error. So the mean squared error is the sum of squared errors divided by n minus 2, which is 18 in this case. It's 0.289651. And there it is in the analysis of variance table in the mean square column and the error row, 0.290, rounded off to 3 decimal places. And then if I do one final calculation, I'm going to calculate S. It's the square root of the mean squared error. Okay, and let's just move this graph out of the way. So there we can see it, 0.538193. So it exactly matches up here in the graph and also in the model summary over here, 0.538193. That shows you the calculation. And then in terms of the interpretation, we can think of this, remember it's the estimated standard deviation of the errors. It's telling us roughly, on average, how far away the points are from the line in the vertical direction. So if the points were further away from the line than they are in this graph, then S would be a larger number. So let's actually see that in another example. I've got a second data set here, y2 and x2. So I'm going to do a fitted line plot for y2 and x2. And this example, the regression standard error is going to be larger because the points are going to look as if they're further away from the line than in this graph. So let's take a look at that. So there we can see, on average, the points are further away from the line than they are in this graph. And you can see the value of S is larger. It's 1.40839 in this case. Okay, so that's a discussion of the calculation and the interpretation of the regression standard error, or S.